So far you have learnt about surfactants. They are the surface active agents when present at low concentrations in a system adsorbs onto surface or interface significantly changing the surface or interfacial free energy. When surfactant molecules are dissolved in water at concentration above the critical micelle concentration, they form aggregates known as micelles. A micelle is an aggregate of surfactant molecules dispersed in a liquid colloid. A typical micelle in aqueous solution forms an aggregate with the hydrophilic head regions in contact with surrounding solvent, forming an outer shell, the nonpolar or hydrophobic single tail regions in the micelle center. The critical micelle concentration is the concentration above which the micelle formation takes place and all added surfactants go to the micelles. It is the exact concentration at which aggregates become thermodynamically stable and soluble in an aqueous solution. The micellization process in water results from the delicate balance of intermolecular forces including hydrophobic, steric, electrostatic, hydrogen bonding and van der Waals interactions resulting in different shape and size of micelle that you have already studied. Now you will study how the various factors such as temperature, chemical structure, electrolyte affects the process of micellization and CMC values. Micelle shape and size can be controlled by changing the surfactant chemical structure as well as by varying solution conditions such as temperature and addition of electrolytes. Let us see the effect of temperature on the CMC values. The effect of temperature on the CMC values varies with the type of surfactant molecule. Temperature has a comparatively small effect on the micellar properties of ionic surfactants. This is very well shown from the graph of the CMC of sodium dodecyl sulfate, that is SDS versus temperature, shown in figure 1. The CMC varies in a non-monotonic way by 10 to 20% over a wide range. The shallow minimum around 25 degrees centigrade can be compared with the similar minimum in the solubility of hydrocarbons in water. The decrease in solubility of hydrocarbon increases the tendency of respective surfactant molecules to form micelles. You can see from this figure the temperature dependence of the CMC of sodium dodecyl sulfate and penta-ethylene glycol mono diacetyl ether. Non-ionic surfactant of the polyoxyethylene type deviate from this behavior and show typically a monotonic and much more pronounced decrease in CMC with increasing temperature. Aqueous solution of many non-ionic surfactants become turbid at a characteristic temperature called the cloud point. The cloud point of a fluid is the temperature at which the dissolved solids are no longer completely soluble, precipitating as a second phase, giving the fluid a cloudy appearance. At temperatures up to the cloud point, there is an increase in micellar size and a corresponding decrease in CMC. Now we will see how the solubility of surfactants be strongly temperature dependent. There are many important and intergoing temperature effects in surfactant self-assembly. One, which is of great practical significance, is the dramatic temperature dependent solubility displayed notably by many ionic surfactants. The solubility may be very low at low temperature and then increase by orders of magnitude in a relatively narrow temperature range. The phenomenon is generally denoted as the Kraft phenomena, with the temperature for the onset of the strongly increasing solubility being known as the Kraft point or Kraft temperature. The temperature dependence of surfactant solubility in the region of the Kraft point is illustrated in the figure. The Kraft point may vary dramatically with subtle changes in the surfactant's chemical structure. There are some points that can be made for alkyl chain surfactants. Number 1. The Kraft point increases rapidly as the alkyl chain length increases. The increase is not regular but displays an odd even effect. Number 2. The Kraft point is strongly dependent on the head group and counter ion, but there are no general trend for the counter ion dependence. Salt addition typically raises the Kraft point while many other co-solute decreases it. You can see from the figure we have plotted the concentration on y-axis and the temperature on the x-axis, and see as at the Kraft point there is a sharp rise in the solubility of the surfactant. Now we will see the effect of chemical structure on the CMC values. Effect of chemical structure on CMC values for some selected surfactants is given in table 1. And a similar list for some non-ionic surfactant is given in table 2. There are some journal remarks about the variation of the CMC with the surfactant chemical structure. Number 1. The CMC decreases strongly with increasing alkyl chain length of the surfactant. For example, an increase in the ethylene oxide chain length of a non-ionic surfactant makes the molecule more hydrophilic and the CMC increases. This is being shown in figure 3 and 4, and the results are given in table 3. As you can see from this figure that the logarithmic of CMC values varies linearly with the number of carbon atoms in the alkyl chain of a surfactant. As you increase the number of carbon atoms in the alkyl chain, there will be more drop in the CMC values. Another figure shows the logarithm of CMC versus the number of carbons in the alkyl chain for octyl ethylene glycol monoalkyl ethers at different temperatures. You can see as we change the temperature from 15 to 40, there will be a sharp change in the CMC value. Second point, non-ionic surfactants generally have much lower CMC values and higher aggregation numbers then their ionic counterparts with similar hydrocarbon chains. You can see from table 2 the CMC values of non-ionic surfactants are given in micromolar, whereas for ionic surfactants the molar concentrations are reported in table 1. Third point, the log of CMC for compounds with identical polar head groups is expressed by the linear equation log of CMC is equals to A minus B into Nc, where Nc is the number of carbon atoms in the chain and A and B are the parameters for a homologous series. The CMC decreases strongly with alkyl chain is shown in table 3. The decrease follows the relationship log CMC equals A minus B into Nc to a good approximation. Fourth point, besides the major difference between ionics and non-ionics, the effect of the head group are moderate. Cationic typically have slightly higher CMCs than anionics. For non-ionics of the oxyethylene variety, there is a moderate increase in the CMC as the polar head becomes larger. Fifth point, the valency of the counter ions have significant effect on CMC, while simple monovalent inorganic counter ions give roughly the same CMC. Increasing the valency to 2 gives a reduction of the CMC by roughly a factor of 4. Sixth point, micellar size increases for a particular cationic surfactant as the counter ion is changed according to the series chloride less than bromide less than iodide, and for a particular anionic surfactant according to sodium less than potassium, which is less than cesium. Next point, ionic surfactants with organic counter ions, example mallates, have lower CMCs and higher aggregation numbers than those with inorganic counter ions. Next, we see that while alkyl chain branching and double bonds, aromatic groups or other polar character in the hydrophobic part produce sizable change in the CMC, a dramatic lowering of the CMC 1 or 2 orders of magnitude results from perfluorination of the alkyl chain. Partial fluorination, interestingly, may increase the CMC. Example, the fluorination of the terminal methyl group roughly doubles the CMC value. The anomalous behavior of partially fluorinated surfactant is due to unfavorable interactions between hydrocarbon and fluorocarbon groups. Now we will see the effect of electrolytes. The addition of electrolyte have significant effect on the CMC of ionic surfactants. This is shown in figure 5 for the addition of 1:1 inert electrolyte to a solution of a monovalent surfactant. This figure shows the effect of sodium chloride addition on the CMC of different sodium alkyl sulfates. The solid lines are predictions of electrostatic theory. Cs is the salt concentration. Electrolyte addition to solution of ionic surfactants decreases the CMC and increases the micellar size. This is because At high electrolyte concentration, the micelles of ionic surfactants may become non-spherical. Salt addition gives a dramatic lowering of CMC, which may amount to an order of magnitude. The effect is moderate for short chain surfactants but is much larger for long chain ones. As a consequence, at high salt concentrations, the variation of CMC with the number of carbons in the alkyl chain is much stronger than without added salt. The rate of change at high salt concentration becomes similar to that of non-ionics.
Now we will see how the size and structure of micelle varies. The driving force of micelle formation is the elimination of the contact between the alkyl chains and water. The larger a spherical micelle, then the more efficient this is, since the volume to area ratio increases. Decreasing the micelle size always leads to an increased hydrocarbon water contact. However, if the spherical micelle was made so large that no surfactant molecule would reach from the micelle surface to the center, one would either have to create a void or some surfactant molecules would lose the contact with the surface. However, if the spherical micelle was made so large that no surfactant molecule would reach from the micelle surface to the center, one would either have to create a void or some surfactant molecules would lose the contact with the surface, introducing polar groups in the center. Both alternatives are unsatisfactory. We should note that the fact that the micelle radius equals the length of an extended surfactant molecule does not mean that the surfactant molecules are all extended. Only one molecule needs to be extended to fulfill the requirements mentioned, and the majority of the surfactant molecules are in a disordered state with many Gauquet conformations. Spectroscopic studies have been used to characterize the state of the alkyl chains in micelles in detail. This state indeed is very close to that of the corresponding alkane in pure liquid oil. At the surface of the micelle, we have the associated counter ions, which in number amount to 50 to 80% of the surfactant ions. As seen above, a number quite invariant to the conditions. Simple inorganic counter ions are very loosely associated with the micelle. The counter ions are very mobile, and there is no specific complex formed with a definite counter ion head group distance. Rather, the counter ions are associated by long range electrostatic interactions to the micelle as a whole. They remain hydrated to a great extent. Cations especially tend to keep their hydration shell. Some water of hydration is thus accounted for by the associated counter ions, and furthermore the polar head groups are extensively hydrated. The micelle size, as expressed by the radius of a spherical aggregated, may be obtained inter alia from scattering experiments. and from Micelle self-diffusion. A related and equally important characteristic of a Micelle is the Micelle aggregation number. As told earlier to you, it is the number of surfactant molecules in one Micelle. This is best determined in fluorescence quenching experiments. Let us take an example. The aggregation number of SDS Micelles is at 60 to 70. The aggregation numbers deviating markedly from the average, the probability is very small. Let us now see a geometrical consideration of chain packing, which is very useful. Based on the geometry of various micellar shapes and the space occupied by the hydrophilic and hydrophobic groups of the surfactants, it is possible to estimate the structure of a Micelle. Since the cross-section area per chain decreases radially towards the center, only one chain can be fully extended, while the others are more or less folded. The aggregation number n can be expressed as the ratio between the micellar core volume and the volume V. This volume V, it corresponds to the volume of the hydrophobic group in the micellar core, that is volume of one chain. And see in the following equation, we have n is equal to ratio of these two parameters, where r mic is the radius of the Micelle. As we all know, volume can be expressed as 4 by 3 pi r cube. We can also express the aggregation number n as the ratio between the micellar area and the cross-sectional area A, which is the area of one surfactant molecule as observed in the equation, and can also be written as A mic upon small a. Putting these aggregation numbers as equal, we obtain the following equation. Since R cannot exceed the extended length of the surfactant alkyl chain, we have L max, and as shown in the equation, therefore, this is less or equal to 1/3 for a spherical Micelle. The ratio V upon L max, this which gives a geometric characterization of a surfactant molecule, will be seen to be very useful when discussing the type of structure formed by a given amphiphile. This is denoted as the critical packing parameter, or it is also called the surfactant number and noted as CPP. Accordingly, the parameter volume upon L max A can determine the shape of the Micelle, where volume V corresponding to the volume of the hydrophobic group in the micellar core, L max the length of the hydrophobic group in the core, and A the cross-sectional area occupied by the hydrophilic group at the Micelle solution interface. According to Stanford, V is equal to 27.4 plus 26.9 Nc angstrom, where N is the number of carbon atoms in the chain less 1 and L max is equal to 1.5 plus 1.265 Nc angstrom, depending upon the extension of the chain. Therefore, for a fully extended chain, L max is equal to 1.5 plus 1.265 N angstrom. Table represents the correlation between the parameter and the structure of the micelle. As you can see, the highest ratio brings the laminar shape, that is half to 1, and when the ratio is between 1/3 to half, we have cylindrical shape, and the lowest is between 0 to 1/3, we get a spherical shape. These are the, for reverse micelle in nonpolar medium, the ratio is less than 1.
Now let us summarize what we have learned. There are many factors that control the shape, size and CMC of micelles. Effect of temperature on the CMC varies with the type of surfactant molecule. The CMC of ionic surfactant varies in non-monotonic way, whereas for non-ionic surfactant it varies in monotonic way, that is, decrease in CMC with increasing temperature. The CMC decreases strongly with increasing alkyl chain length of the surfactant. Non-ionic surfactants generally have very much lower CMC values and higher aggregation number than their ionic counterparts with similar hydrocarbon chains. The electrolyte addition to solutions of ionic surfactants decreases the CMC and increases the micellar size. Micelle formed by non-ionic surfactant have hydrophobic core surrounded by shell composed of polyethylene oxide chain. No counterions are present in it. The shape and structure of micelle can be estimated by the ratio of V upon L max into A, where V is the volume of hydrophobic group in the micellar core, that is, the volume of one chain. L max is the extended length of the surfactant alkyl chain, and A is the cross-sectional area of one surfactant molecule.